Imagine you're cruising down the highway on a rainy evening, right?
Okay.
You're in a brand new electric vehicle. You're doing maybe 80 miles an hour.
Yeah.
The cabin is completely silent. The heater is running. Maybe you have an audio show playing in the background.
Setting a nice scene.
Right. It's peaceful.
Yeah.
From where you're sitting, everything feels calm and perfectly safe. But beneath the floorboards, like literally inside the casing of the motor, there is an absolute physical war going on.
Oh, yeah. A violent one.
Yeah, exactly. You have hundreds, sometimes over 1,000 volts of electricity just desperate to find a path to the ground. And the only thing stopping that massive amount of energy from turning the entire metal frame of your car into a lethal conductor.
Which would be catastrophic.
Right. The only thing stopping that is a layer of polymer plastic that is sometimes thinner than a human hair.
It's wild to think about.
It really is. And if that microscopic layer of insulation fails, you don't get like a polite warning light on your dashboard with a few minutes to pull over safely.
No, not at all.
You have literal milliseconds to prevent the entire system from experiencing a catastrophic failure.
It's a terrifying reality if you look at it purely from a physics standpoint.
Yeah.
I mean, in the automotive engineering world, this specific hazard, what we call low insulation resistance in a high voltage motor.
Okay.
It's classified as an ASIL D functional safety target.
ASIL D, that's pretty high up there, right?
It is the highest, it's the most stringent hazard risk classification that exists in the industry.
Wow.
Yeah, it essentially dictates that the risk of fatal injury, whether that's through, severe electrocution or a cascading thermal explosion, is so incredibly high that the system requires absolutely bulletproof fail-safes.
And that is exactly our mission for this deep dive today. We are looking at a highly technical, honestly, incredibly dense set of engineering sources to kind of decode the invisible shield protecting you in a modern EV.
It's fascinating stuff.
It is. We want to understand the obsessive levels of fail-safes, the microscopic physics, and just the extreme manufacturing required to keep thousands of volts safely contained. Because once you understand what is actually happening inside that motor, it completely changes how you look at the machine in your driveway.
Absolutely.
Yeah.
And to really appreciate those defenses, we have to start by understanding the attack.
Right.
Right. What are we defending against?
Exactly. We have to look at the root causes of why this insulation fails in the first place. The source material outlines 4 distinct physical and chemical forces that are constantly, and I mean constantly, trying to break down the motor's defenses.
Like the 4 horsemen of the electric motor apocalypse.
Yeah, that's a good way to put it. You can think of them as the 4 primary forces of degradation.
So let's get into those, because the first one listed is purely electrical, and it's tied directly to how modern EVs get their incredible range and performance.
Yeah. The sources point specifically to silicon carbide inverters. Now, I know these are like the gold standard for efficiency in EVs, but it seems like that efficiency comes with a pretty dangerous side effect.
It does, yeah. So silicon carbide, or sync chips, they're incredible because they can switch power on and off exceptionally fast, like unbelievably fast.
How fast are we talking?
We are talking about voltage rising at a rate of 10 kilovolts per microsecond.
Wait, per microsecond?
Yes, that is 10,000 volts pushing through the system in a single millionth of a second.
10,000 volts in a millionth of a second. I can't even conceptualize speed like that. I mean, when you pump electricity into a wire that aggressively, I imagine it doesn't just flow smoothly like water out of a garden hose.
No, definitely not. A much better analogy would be, think of a highly pressurized water system in a massive skyscraper.
Okay.
If you slam a massive valve shut instantly, the water doesn't just politely stop, right? The kinetic energy slams into the pipe. It creates this massive pressure wave that ripples backward. Plumbers call it a water hammer.
Oh, right, when the pipes violently shake and bang behind the wall.
Exactly. Now apply that to an EV motor. These incredibly fast switching speeds create high voltage reflection waves.
Okay.
You basically have electrical pressure waves slamming into the first few turns of the copper wire inside the motor.
And if that electrical pressure is too high for the plastic insulation that's wrapping those wires, what happens? Does the electricity just punch a hole right through it?
Not immediately, no. It's more insidious than that. It creates a phenomenon called partial discharge.
Partial discharge. Okay, what is that?
It's a localized microscopic breakdown. So the electric field becomes so intense that it ionizes the tiny, tiny molecules of air resting right on the surface of the plastic.
Oh, wow.
Yeah, it literally creates microscopic sparks on the outside of the wire.
Just constantly sparking against the plastic. Are those sparks physically damaging
But
us?
severely. The sparks generate ozone, they create concentrated points of extreme heat, and they essentially bombard the polymer with high-energy electrons. The industry refers to this as corona aging. It basically carbonizes the plastic, taking these microscopic bites out of the insulation over time until it finally cracks.
Okay, so you have thousands of microscopic sparks slowly eating the insulation. That is just the electrical attack. But the source material immediately follows that up with a second force, which is thermal aging, just the pure heat of the motor itself.
Yes. And the terrifying part is that they act as a multiplier for one another.
Oh, great.
The source references the Arrhenius equation, which is a fundamental principle in physical chemistry.
Let me guess. Heat makes things worse.
In simple terms, yes. It dictates that heat exponentially accelerates chemical degradation. And an EV motor under a heavy load, say you're driving up a steep mountain pass or you're accelerating really hard onto the highway,
Yeah.
it can easily reach internal temperatures of 130 to 150 degrees Celsius.
So you are baking the plastic at around 300 degrees Fahrenheit while simultaneously shooting it with microscopic electrical sparks.
Exactly. And at those temperatures, the polymers start to oxidize. They dry out, they lose their molecular flexibility, and they just become incredibly brittle.
Like leaving a rubber band out in the sun for a year.
Exactly like that. And more importantly, their dielectric strength, which is their innate chemical ability to resist electrical flow drops significantly when they get that hot.
Which makes it even more vulnerable to the sparks we just talked about.
You got it.
I'm really starting to see how these forces compound. But the third factor mentioned in the sources, this one really caught my attention. It's thermal mechanical abrasion.
Right.
I never really thought about a solid block of metal and plastic shifting around. But apparently the different materials inside the motor are expanding at different rates.
Yeah, this is one of the most persistent headaches in mechanical engineering as a whole.
How so?
Well, you have a stationary motor core made of steel. Inside that steel, you have copper wires. And holding those wires in place, you have a cured resin.
Okay, 3 different materials.
Right. And every single one of those materials has a completely different coefficient of thermal expansion.
Meaning that when you heat them up to that 150 degrees Celsius, they all swell and grow, but they don't grow by the same amount.
Precisely. The copper gets longer faster than the steel does, for instance.
Wow.
Now imagine a vehicle starting up in the dead of winter. It's negative 40 degrees outside.
Okay.
You start driving, and under heavy acceleration, it heats up to 150 degrees.
That is a massive temperature swing.
Right. So all these materials are expanding and contracting at completely different rates. They are essentially fighting each other. And this creates massive shear forces on a microscopic level.
Oh, I see.
The copper wire is physically trying to slide against the hard resin in the steel, add in the high-frequency vibration from just spinning the wheels at highway speeds, and you get this continuous microscopic rubbing.
It's grinding the protective enamel off the wire like ultra-fine sandpaper.
Exactly. So you have the electricity bombarding it with sparks, the heat baking it dry, and the mechanical vibration physically grinding it away.
And if that isn't enough, there is a fourth force at play here. The source calls it electrochemical migration.
Yes.
And this seems to be what happens when the outside environment manages to actually breach the physical casing of the motor.
Right. So the motor relies on heavy-duty seals, usually specialized O-rings, to keep the internal environment completely pristine. But seals naturally degrade over a vehicle's lifespan.
Sure, rubber gets old.
Yeah. And if they weaken, contaminants slip past. It could be moisture from just high humidity or salt spray kicked up from winter roads, or even transmission cooling oil that contains microscopic metal shavings from the gears.
Wait, if you introduce salt water or metal shavings into an environment that is currently humming with 800 volts of electricity, I mean, what actually happens?
It drives a violent electrochemical reaction. The intense electric field forces the moisture and the microscopic metal contaminants to bond and literally grow.
Grow.
Yeah, they form what we call dendrites.
Dendrites, like tree branches.
Visually, yes, exactly like that. They look like tiny metallic tree branches growing outward from the motor core toward the bare copper wire, or vice versa.
Like frost growing on a window, but made of conductive metal.
Perfect analogy. The high voltage is essentially forcing a metallic bridge to build itself right across the gap. And once that dendrite bridge connects the live wire to the steel core.
The electricity suddenly has a shortcut.
Exactly. It bypasses the insulation entirely.
and your electrical resistance drops off a cliff, turning the frame of the car into a live wire.
Yeah.
Man, when you lay it all out like that, the sparks, the baking heat, the grinding friction, and these literal metallic tree branches trying to short-circuit the system. It feels like a miracle these motors survive a single road trip, let alone a 10-year lifespan.
It really emphasizes why the vehicle cannot just wait for a total failure to occur.
Right.
The car needs an incredibly perceptive internal monitoring system to catch these microscopic breakdowns long before they turn into a catastrophic event.
And that leads perfectly into the second major area of our deep dive today, which is the technological architecture and diagnostics.
The digital immune system.
Yes, the car's digital immune system. Because relying on a dashboard light isn't going to cut it here. The source material outlines a multi-layer diagnostic system.
It does.
So let's start with the baseline defense, which they call active insulation monitoring, or the IMD. How does a car actively check its own insulation while you're driving it down the highway?
So the IMD sits on the high-voltage DC bus. Those are the main power arteries between the battery pack and the motor.
Okay.
It actively injects very low-frequency electrical signals directly into the metal chassis of the car, and then it measures what comes back.
So it's actively poking the system.
Yeah, it's using those pulses to mathematically calculate the total isolation resistance of the entire vehicle.
So it's constantly pinging the frame to see how difficult it is for electricity to leak out. And there are strict safety thresholds here. The source states that if the resistance drops below 100 kilo-ohms, the car triggers a level 1 warning. But if it drops below 10 kilo-ohms, that is considered the fatal threshold.
Right. At 10 kilo-ohms, the system assumes a massive catastrophic short is imminent.
But the IMD is just one layer, right? It's somewhat of a macro-level check.
Yeah, it's looking at the whole system. For micro-level speed, the vehicle utilizes KCL leakage current monitoring. KCL stands for Kirchhoff's current law.
Okay, I'm going to need you to translate Kirchhoff's law for me. What are we actually measuring here?
It's quite elegant, actually. Have you ever balanced a checkbook?
Barely, but yes.
So Kirchhoff's current law simply states that the total current entering a junction must equal the total current leaving it.
Okay.
Think of it like a perfectly balanced financial ledger. Every penny must be accounted for.
Right.
The vehicle is feeding 3 massive power cables into the motor to spin it. The ultra-precise sensors monitor the current on phase A, phase B, and phase C.
Okay, the 3 inputs.
And the software constantly adds them together. Because of how alternating current cycles, the sum of those 3 phases should always be exactly 0.
Rate 0.
Yeah, every drop of electricity that goes in must come back out through the other phases at any given millisecond.
Oh, I get it. So if the sensor adds up the 3 cables and the answer is not 0, it means electricity is missing.
Precisely. If even a few milliamps are unaccounted for, the car knows definitively that those milliamps are leaking through the cracked insulation and into the steel core of the motor.
Wow.
And because this is a fundamental mathematical calculation happening at the absolute lowest level of the hardware, it doesn't take seconds to calculate. The system can detect that milliamp level leak in just 2 milliseconds.
0.002 of a second.
Yeah.
That is unbelievable. But the source material highlights a third diagnostic layer that goes even further. The zero-sequence voltage diagnostics.
Oh, this one is amazing.
And from what I understand, this one isn't looking for a leak that's currently happening. It's trying to predict a leak before it even starts.
This is genuinely the most fascinating piece of software engineering in the entire system. The previous sensors, the IMD and the KCL monitor, they are reactive.
Right. They catch the leak as it happens.
Exactly. They catch the failure as it begins.
Yeah.
The zero-sequence algorithm is predictive. It analyzes the resonant frequency of the high-frequency currents in the system.
Resonant frequency. Let's ground that. Are we talking about vibrations?
Electrical vibrations, yes. Imagine the electrical system as a tightly tuned guitar string.
Okay.
When the plastic insulation is brand new and healthy, those electrical waves vibrate at a very specific expected frequency.
Right.
But as we discussed earlier, the heat and the sparks are chemically altering that plastic over time. As the polymer degrades, its parasitic capacitance changes.
Parasitic capacitance, meaning the plastic's ability to hold an electrical charge is shifting. It's getting chemically spongy before it actually cracks.
That's a great way to put it. The material properties are changing on a molecular level. And when that happens, it alters the electrical resonant frequency of the whole system.
The guitar string goes slightly out of tune.
Exactly. The software is constantly listening to this background electrical noise, and it can mathematically detect that microscopic frequency shift.
Wow.
It knows the plastic is weakening before a single drop of current actually leaks out.
That is wildly sophisticated. It can literally hear the plastic getting tired.
Yeah.
Okay, so the car's immune system is incredibly perceptive, but detecting a failure is useless if you don't do something about it, right?
Right.
What is the vehicle's fallback strategy when these alarms actually start ringing?
So it utilizes a graded fault tolerance strategy, depending on the severity of the alert. If it detects light degradation, like that frequency shifting or a minor resistance drop, it triggers a limp home mode.
The car puts itself on life support.
Yeah, exactly.
The source says it actively derates the thermal and voltage limits. It caps the motor's torque at 30%, and it physically limits your speed to under 40 kilometers per hour.
It's doing everything possible to reduce the heat and the electrical pressure inside the motor so you can safely pull over to the shoulder.
But that is the gentle scenario.
Right.
What happens if an O-ring completely blows out, water floods the motor housing, and the resistance instantly plummets below that fatal 10 kilo-ohm threshold?
The source material is very explicit here. It states the system must execute an FTTI response,
An FTTI.
a fault-tolerant time interval. And it has to execute this in less than or equal to 60 milliseconds.
Less time than it takes to blink your eye.
Literally.
But wait, I have a really hard time wrapping my head around this. Let's say I'm doing 80 miles an hour on the highway. I have thousands of pounds of vehicle moving at high speed, physically spinning that motor.
Yeah.
The motor is acting as a massive generator at this point, pumping out huge amounts of voltage. If you detect a fatal short, how do you safely stop all that energy in 60 milliseconds without causing a massive fire? You can't just flip a switch and disconnect the battery, right?
No, absolutely not.
Why not?
Because if you instantly sever the connection to the battery while the motor is spinning that fast, the kinetic energy has nowhere to go.
Oh, wait.
The motor would generate a massive, uncontrolled voltage spike called back EMF. It would blow the inverters to pieces and likely start a fire right there.
So you can't just cut the cord. What do?
The vehicle executes a maneuver called stepwise active short circuit, or ASC.
Wait. You're saying the safety mechanism to prevent a catastrophic short circuit is for the car to intentionally short circuit itself?
I know, it sounds like
It
madness.
sounds completely counterintuitive.
It does, but it is a highly controlled mathematical short circuit. Instead of disconnecting the motor, the power electronics instantly cross the streams.
Cross the streams, like Ghostbusters.
Basically, they clamp the three main power phases of the motor together.
Why does that help? Doesn't that just fry the wires?
Because it creates a closed internal loop. Instead of the massive energy spike trying to surge back into the sensitive battery in computers, the energy is trapped in a loop within the heavy copper coils of the motor itself.
Oh, because the coils are so thick they can handle it.
Exactly. It safely dissipates that massive electrical energy as heat within the heavy metal casing. It forces the voltage spike to clamp down below 720 volts safely, neutralizing the threat before shutting down the main contactors to the battery.
All in 60 milliseconds.
Every single time.
It senses the water, calculates the speed, intentionally crosses the wires to trap the energy, burns the voltage off as heat, and safely kills the battery. The choreography required to make that happen is stunning.
It is a marvel of software engineering. But any safety engineer will tell you that relying on software diagnostics to save you means you have already failed at the hardware level.
Right. You'd rather it not break in the first place.
Exactly. The ultimate goal is to ensure the physical materials never break down in the first place.
Which brings us to the design phase. The DFMEA, or Design Failure Mode and Effects Analysis.
Right.
This is where they try to build the physical fortress. How do engineers design a motor so those four forces of degradation, the heat, the sparks, the rubbing, the salt just can't win?
They attack the vulnerabilities at the absolute microscopic level, and they start with the copper wire itself. You cannot use standard industrial copper wire in an EV motor.
It wouldn't survive a day.
Exactly. The source specifies the use of highly specialized corona-resistant wire.
Corona, referring to those microscopic partial discharge sparks we talked about earlier, the ones taking microscopic bites out of the plastic.
Exactly. To combat that, the wire is coated in a Class N enamel, meaning it is chemically formulated to operate continuously at 200 degrees Celsius without melting.
200 degrees, that's intense.
But heat resistance isn't enough to stop the electrons. So they dope the enamel with inorganic nanoparticle fillers.
Dope the enamel. So they are mixing microscopic particles into the plastic itself.
Yes. Think of the plastic insulation like a slowing river, and these inorganic nanoparticles are like massive boulders dropped into it.
Okay, I can picture that.
When those high-energy electrons from the partial discharge try to blast their way through the plastic, they smash into these dense, inorganic boulders.
Ah,
The impact energy is completely absorbed, and the electron is deflected.
it's literally wearing microscopic armor.
It is. And the specifications are incredibly rigid. The mathematical design dictates that the wire's partial discharge inception voltage.
Which is what?
It's the absolute minimum voltage required to even begin creating a spark.
Okay.
That threshold must be greater than or equal to 1.5 times the absolute highest voltage spike the inverter could possibly generate, even when the entire system is baking at 150 degrees Celsius.
So they are over-engineering the wire's armor by at least 50% over the worst-case scenario?
Yes.
But they don't rely entirely on the wire, do they? They also build physical walls inside the motor. The source details the use of multi-layer slot liners.
Right. When they insert the copper wires into the steel core, they line the slots with a 3-layer composite paper. The industry standard mentioned is NMN, which stands for Nomex Mylar Nomex.
Okay, what makes that special?
It's a fascinating material because it has extremely high thermal conductivity.
So it pulls the heat away from the wire.
Exactly. But at the same time, it possesses massive dielectric strength to physically block the electricity from jumping to the steel.
So it's thermally conductive but electrically insulating.
Right. And they also use custom 3D preformed paper at the ends of the motor to physically separate the different phases of wire from touching each other.
So they are eliminating any geometric path the electricity could possibly take to short out.
Exactly. But the most elegant design solution in the DFMEA isn't just about building thicker walls.
What is it?
It's about disarming the weapon itself.
Okay, color me intrigued.
We established that the root cause of the partial discharge sparks is the incredibly fast switching speed of the silicon carbide inverter, right?
Right, the 10 kilovolt per microsecond voltage spike. The water hammer.
So instead of just trying to survive the water hammer, engineers integrate a common mode LC filter.
A filter.
It's a specialized passive magnetic ring installed right where the power cables meet the motor. This physical chunk of hardware acts as an electrical shock absorber.
I love this concept. How much does it actually slow the spike down?
It takes that violent 10 kilovolt per microsecond wave, passes it through the magnetic field, and smooths it out, crushing it down to a gentle wave of less than 1.5 kilovolts per microsecond.
That is brilliant. You have a problem created by the high-tech software in the semiconductor chips.
Yeah.
But instead of sacrificing the efficiency of the software by slowing the chips down, you install a passive physical ring that absorbs the shock. You're literally altering the laws of physics inside the motor so the partial discharge sparks don't even have enough energy to form.
It is the perfect marriage of hardware and software co-design.
It really is. But designing this perfect nanoparticle-armored, magnetically filtered motor on a computer screen is one thing, right?
Oh, absolutely.
Actually manufacturing it is an entirely different beast. How on earth do you guarantee that a massive automotive factory can assemble this perfectly, thousands of times a day, without introducing a single microscopic flaw?
This is where we get into the domain of PFMEA,
Process failure mode and effects analysis.
process control on the assembly line. Because all of that nanoparticle armor is completely useless if a robotic arm scratches it during assembly.
Right, and the source gets incredibly specific here about the machinery used. To get the wire into the steel core, they use a machine called a needle winder.
Yes.
But the tension on the wire must be controlled to within exactly plus or minus 1 Newton.
1 Newton of force. To put that in perspective, that is roughly the force required to hold a medium-sized apple in your hand.
Wait. On heavy industrial manufacturing equipment, pulling thick copper wire off a massive spool at high speeds, they have to maintain a tension tolerance of an apple.
Yeah.
Why does it have to be that precise?
Because of friction. If the machine pulls the wire even slightly too tight as it forces it into the steel slot, it will drag against the metal and scratch the armor. That drag will create microscopic scratches in the nanoparticle enamel. If you thin the armor by even a fraction of a millimeter, the electrical field will mathematically concentrate on that weak point, and the insulation will fail years prematurely.
So they essentially have to handle this heavy copper wire with the delicacy of glass.
Exactly. And once the pristine wire is successfully wound into the motor, it has to be locked into place with a liquid resin.
Right, to stop the vibration.
But you can't simply pour resin over it and let it dry.
Yeah.
The source dictates a mandatory process called vacuum pressure impregnation, or VPI.
This part of the source material was fascinating to me because the entire goal of this complex VPI process is to eliminate air bubbles.
Yes.
And I have to stop and ask, is an air bubble really that dangerous? Like a single tiny pocket of air trapped inside the resin of this massive heavy metal engine can actually total the vehicle?
It sounds absurd, but physically, yes. Think about the physical properties of air versus solid plastic. Air is a much, much weaker insulator. So if you have a microscopic air bubble trapped inside the plastic resin and a massive electric field passes through it, the solid plastic handles the stress perfectly fine.
Right.
But the air inside that tiny void cannot handle it. The gas inside the bubble actually breaks down and turns into plasma.
Plasma. So you essentially get a localized microscopic lightning storm trapped inside the bubble.
Exactly. And over years of driving, that trapped lightning storm slowly scorches the plastic walls of the bubble, burning away the material, making the cavern bigger and bigger until it eats all the way through to the copper wire and causes a fatal short.
That is terrifying. Just an invisible lightning storm eating the motor from the inside out.
Yeah.
Okay, so how do they guarantee there are zero microscopic bubbles in a mass-produced motor?
Through the extremes of pressure. First, they place the entire motor assembly into a sealed chamber and pull a near vacuum.
Like space vacuum.
Almost. They drop the ambient pressure down to less than 10 millibars. This physically sucks every microscopic pocket of trapped air out from between the thousands of individual wires.
And then, while it is still in a vacuum, they introduce the liquid resin.
Right. But they don't just let it settle. They hit the chamber with extreme high pressure, greater than 6 bar.
Wow.
They violently force the liquid resin deep into every single microscopic crevice where the air used to be, ensuring a completely solid, void-free matrix.
And the craziest part is they don't even trust that process completely. The source states they use a 3D industrial CT scanner, like a medical CT scan, to physically look inside the solid metal and resin to prove there are absolutely zero voids.
Because if a void exists, the motor is useless.
Okay.
And to verify the electrical integrity on the assembly line, they mandate a 100% online PD and surge test.
Right. They hook up this freshly built motor and blast it with over 2,500 volts of electricity right there in the factory.
Yeah.
They're intentionally trying to break it.
They blast it, and highly sensitive sensors listen for the escape of even 10 picocoulombs of electric charge.
What is a picocoulomb?
It's a trillionth of a coulomb. It's a vanishingly small measurement of electricity. But if the sensors detect even a whisper of a spark, it means there is a microscopic flaw that the CP scanner somehow missed, and the motor is scrapped.
Scrapped, just like that.
Just like that. And to protect against that final threat, the electrochemical migration, the water and oil creeping in, they had to seal the exterior perfectly.
So how do they test that?
They use robotic servo presses to perfectly crush the FKM O-rings into place. And to prove the seal is absolute, they fill the motor casing with helium gas.
Why helium?
Because helium atoms are incredibly small. The logic is simple. If a microscopic helium atom cannot escape the casing, then water molecules and transmission oils certainly cannot get in.
The leak rate tolerance they demand here is less than 1 × 10 to the -5 millibars liter per second. I don't even know how to visualize a leak that tiny, but it implies the motor is hermetically sealed to the standards of a spacecraft.
It basically is. So at this point, you have a flawless design, and you have an automated factory that has proven it can build that design without a single scratch, bubble, or leaky seal.
Which brings us to the final hurdle, the DVP&R, or Design Verification Plan and Report.
Right.
Because a pristine motor sitting on a factory floor is great, but how do they actually know this fragile nanoparticle armor and perfectly balanced resin will survive a decade of hitting potholes in the freezing rain?
That's the real test.
Oh.
Before a single unit goes into production for consumers, prototype motors are subjected to testing protocols that are legitimately brutal.
Brutal how?
They don't just put it in a car and drive it around a test track. They isolate the motor and actively try to tear it apart using standard tests like VDA 320 or LV 124.
Let's talk about the physical mechanisms of this testing because it sounds like a torture chamber. They start with a thermal shock and vibration test.
Yeah.
They put the motor into a chamber and cycle the temperature from a freezing -40 degrees Celsius to a baking 150 degrees Celsius.
And remember our discussion about the different materials expanding at different rates.
The shear forces.
Exactly.
Yeah.
They are actively trying to use thermal expansion to peel the resin and the copper apart. And while the motor is freezing and expanding, they have it bolted to a shaker table, vibrating it violently in 3 different axes.
With a gravitational force equivalent to 35 meters per second squared.
Right.
So they are trying to rip the internal components apart through sheer gravitational and thermal stress. And while it's freezing, baking, and shaking, they are powering it up.
They are continuously blasting it with that massive electrical stress, the full 10 kilovolt per microsecond switching voltage, just to force partial discharge.
And they do this continuously for over 1,000 hours.
Over 40 days of continuous, extreme physical and electrical stress. And once that 1,000 hours is up, they dismantle the motor, they put the copper wire under microscope, and the nanoparticle enamel is not allowed to show a single micro crack. No carbonization marks, and no separation between the layers. Its electrical resistance must remain perfectly intact.
And that's just the internal endurance test. They also test those hermetic seals, the IP69K and salt spray tests.
Yeah, they are actively trying to force the electrochemical migration, the dendrite growth we discussed.
How to do that?
They place the motor in a chamber at 85 degrees Celsius with 85% humidity for 100 cycles. Then they move it to a salt spray chamber for 96 hours, simulating a lifetime of driving through deep puddles of road salt.
And then they hit it with a high-temperature, high-pressure pressure washer. The IP69K standard basically means it has to survive a direct assault from an industrial steam cleaner.
Exactly. And after all of that moisture and pressure, they run 500 volts of direct current right through the casing.
And the insulation resistance must remain firmly above 100 megaohms. But the truly impressive part is when they unbolt the casing. After a month of salt fog and direct steam cleaning, the interior of the motor must be 100% bone dry. If there is a single drop of condensation inside, it fails.
It really puts into perspective the sheer structural integrity of these systems. We often hear a lot of anxiety from the public regarding the safety of high-voltage electric vehicles in crashes or floods, but when you examine the violence of the validation standards they must pass, the engineering is incredibly robust.
It is, but there is one final exam in the source material. Because the engineers have proven the physical hardware is indestructible, but they still have to prove that the software, the digital immune system from earlier, will actually work in the real world when things go catastrophically wrong.
Right, the software has to act perfectly.
So they run a hardware in the loop, or HEL fault injection test.
This is the ultimate proof of concept. They intentionally sabotage a running system.
They mount the motor on a high-fidelity test rig. They power it up and spin it to an insane 12,000 revolutions per minute at maximum electrical load. The motor is literally screaming.
Yeah.
And then, without warning, the engineers trigger a switch that uses a specialized resistor card to artificially drop the motor's internal insulation resistance instantly down to 5 kiloohms.
Which, as we established earlier, is well below the 10 kiloohm fatal threshold.
Right. They are actively tricking the vehicle's computers into believing that it just suffered a massive catastrophic internal short circuit while traveling at over 100 miles an hour.
And what happens in the subsequent fractions of a second dictates whether the vehicle receives its ASIL D safety certification.
The system must flawlessly execute everything we talked about.
Every single step.
The software has to detect that resistance drop, recognize the severity, and trigger the FTTI response.
Yeah.
It must command the inverters to execute the stepwise active short circuit, perfectly crossing the streams to safely swallow the massive back voltage. It has to clamp the DC bus down below 720 volts and transition that 12,000 RPM motor into limp home mode without blowing up the power electronics or violently locking up the wheels.
And it must perform this entire symphony of physical and software interventions in less than 60 milliseconds, every single time, without fail.
When you pull back and look at the entire journey we just took through these sources, it is genuinely staggering. I mean, we started at the absolute microscopic level, looking at an visible chemical degradation, temperature expansions, and ozone taking bites out of polymer chains.
Yeah, we examined how software algorithms calculate milliamp leaks in 2 milliseconds.
Right.
And how engineers deploy inorganic nanoparticle armor and zero-bubble vacuum chambers to basically bend the laws of physics to their will.
And finally, we saw them throw the entire assembly into a freezing, shaking, salt-spraying torture chamber while spinning at 12,000 RPM, just to prove that the invisible shield holds.
It serves as a really powerful reminder that true safety in the modern era isn't just about, a thick piece of reinforced steel.
No, not anymore.
It is a deeply integrated, complex ecosystem of chemistry, physics, material science, and software, all communicating perfectly in real time.
The next time you press the accelerator in an EV, or even just see one silently glide past you on the street, I highly encourage you to remember this. because underneath that quiet, serene exterior, there's a microscopic war raging, and just a breathtaking symphony of engineering keeping it all perfectly, safely contained.
If I may, the source material sparked a thought that I want to leave everyone with.
Yeah, please.
We discussed the zero-sequence voltage monitoring earlier, right? The algorithm that listens to the resonant frequency shifting, acting like a guitar string going out of tune as the plastic degrades.
Right, the system that can detect the plastic getting spongy before it actually breaks.
Exactly. The engineers currently use complex data tools to build mathematical models of those shifts.
Yeah.
But if we connect this to the broader trajectory of technology, what happens when we apply advanced AI and machine learning to that non-invasive, high-frequency data in real time across a fleet of millions of vehicles?
Oh.
Could future vehicles learn the unique microscopic electrical signature of their own specific motors? We might be moving toward a horizon where a car can predict its own physical hardware failures months before a human or even a traditional threshold sensor ever realizes there's a microscopic problem. We are transitioning from vehicles that react to failures in milliseconds to vehicles that conceptually heal themselves by predicting the failure before it even begins.
Now that is a profound thought to end on. Predictive, AI-driven microscopic safety. It proves that the invisible shield protecting us is only going to get smarter, faster, and more perceptive. That is all for today's deep dive into the high-voltage trenches. Stay curious, keep questioning the complex world around you, and we'll catch you on the next one.